In this video, we're going to discuss how to impose a design constraint on constraint force. Or another way of saying this is, I want to impose a design constraint on the support for this 1 degree of freedom system. Here on this plot, I have a time history of the force on the support. You can see that our minimum constraint force, if you will, is approximately 175 newtons. And our maximum constraint force is about 200 newtons. So now, here in blue is my goal. I want to say that the force on the constraint or the support is not allowed to go beyond 250 newtons. Here in blue is the final design's constraint force, if you will. This plot is actually mislabeled. It should say constraint force, not force and spring. Here, feel free to pause the video, check out the specs of this 1 degree of freedom system. I have the value for K, the mass, the point mass, and so on and so on. As for a problem statement, same as before in my previous videos, we're minimizing the cost of the spring. We're letting the stiffness of the spring vary. But our design constraint, again, we're going to say out of all the time points, out of all the forces on the constraint, find the maximum, constrain that one, and make sure it never goes beyond 250 newtons. Now let's go ahead and walk through this with MSC Nastran. I've already taken time to create my design model, so I have this folder optimization with my PDF file. I already have statements for the design variable and the design objective. I just have to create my constraint. So let's go ahead and click on constraints and switch this to modal transient. And I'll scroll through the list of available constraint types and I'll look for single point constraint force. If I select that one time, I can now, or rather, once I click this, it allows me to create my design constraints. And here I just want one, so I'll delete all of them but one. I can now start adjusting my design constraint. The first thing I'll do is I'll assign the upper bound or upper limit for the design constraint. I'll type in a value of 250 point here. So this would be my 250 newtons. Here I'm doing this for grid or node 2. As for the SPC force component, we now have to look, or rather that is using the same convention as if you were imposing a displacement constraint. So the 1 component will correspond to the X, the 2 component will correspond to the Y, and so on and so on. Here in Patron, I have my model already set up. This point is fixed. This point is my mass. So you can imagine this mass oscillating vertically up and down. This is node 1, node 2. So this is going to be oscillating in the X direction. So the support will have a reaction in the 1 or X component. So we'll type in a 1 here. As for the time value, if you've seen my previous video, you've seen me discuss the use of min, RSS, SSQ, and so on and so on. Here, I'll type in a value of max. What this will do is it will go ahead and search every single time point, and whichever point is the maximum, it will constrain that point for the respective design cycle. With each design cycle, the peaks might change. So for the next design cycle, the peak at 0.3 seconds might be higher. So then it would constrain that point for that design cycle. It might change for the next design cycle, so the point constraint might be different. Back in the web app, in my output are my new statements for my design model. So these statements define the design constraint. I can copy and paste those design constraints here in my BDF file And now, since most of the model I've already completed before the video, I can go ahead and perform my optimization. And while that's happening, let me make a brief comment. As always, my email address is here, bottom right hand corner. Feel free to reach out to me if you want support, guidance, you want more training, you want access to this web app for Solution 200. I'd be more than glad to reach back out to you and discuss how to make this happen for you. Now, my optimization is complete. Let's scroll to the bottom and make sure optimization successfully went through. Okay, I see the successful message. Let me look at the objective values for a moment and make sure these are the same ones I have in my problem statement here. And now it seems that I've made a slight mistake here. Just give me a moment while I look at this and see what happened. It might be worth actually let me discuss what's happened. At the beginning of our analysis, we started with a design that had a spring value of 2,000 newtons per meter. But now the new spring value is spring stiffness actually is 0.01 newtons per meter. So now I'm kind of asking what went wrong with my optimization in this case. What I'll do is I'll look through the history of the design cycles. And here, let me scroll through until I find the first section called Design Cycle 1. So here's Design Cycle 1. There's a section called Design Constraints on Responses. I'm looking to find the one with the asterisk indicating that there's been, that's the maximum constraint. And here I see that my maximum constraint is on an equation response, which is kind of odd because I impose this directly on a response. So let's go ahead and see if we can locate which one's the problematic one. Oh yeah. So the response type is equation, EQUA, because we use the max value here. And here, let's go ahead and see if we can find any value here. And let me trace this back. So we're looking for an internal response ID of 1. And here I see that, well, you see one thing right off the bat. You'll see that all my input values are 0. Whereas my time plot shows me that the constraint force is actually not 0 for all the time steps. So I have definitely misconfigured my design constraint here. Let's go ahead and look back at my constraint, how I set it up here. So we're doing this in the X direction. We're doing this for the max. For ATTI, that would be node 2. Oh, that's where it went wrong. Node 2 is the node at the mass, and that point is not constrained. Hence, we won't have a constrained force. It should have been node 1 that I've constrained. So let's go ahead and type in node 1 here. We'll take these original outputs, and since they've been updated, let's go ahead and copy those to my design model. Go ahead and replace the old ones. And then I'll delete the old optimization files and redo the optimization. There's another separate video I have that walks you through the process of verifying that you've properly constrained your results and your responses. Here, what I just did on the right was a small glimpse of what the troubleshooting process will look like. You can see now that my input values for the responses are now non-zero. So these values should be the same values as the ones for my graph, indicating I've properly set up the design model. Let's go to the bottom and see if I've got what I wanted to achieve. So the $10 and the $4.72. Okay, perfect. So the results are in line with what I planned 4. Let's go ahead and discuss the results. So we started at initial design with a spring constant of 2000 newtons per meter. Our final spring stiffness is 945 newtons per meter. The price is there. What's more interesting is the time history of the force at the constraint. Here in orange is what the initial design previously produced. You can see at approximately 0.6 and 0.625 seconds to produce a maximum constraint force of about 200 newtons. But now, with the new design, the new string, the maximum constraint force is now 250 newtons. And so that basically is how you impose a constraint on a constraint force. I originally went through this issue where I misconfigured my design constraint. I performed a quick troubleshooting step, and that revealed I made a mistake in creating my design constraint. Eventually, we found the issue, we've corrected it, and we finally achieved a successful optimization. And we reached the objective we wanted to reach. And so with that concludes at the end of the video. As always, if you have a question, comment, if you want training, guidance, if you want me to support you on a project of your own, feel free to email me. I'll be more than glad to reach back out to you. Thank you for watching.